All right, I'm going to provide a short, relatively short little video lesson on electric circuits to better illustrate visually for you what I talked about a little bit in class as we were reviewing the MCAS practice exam, relating to the resistance of a circuit. Remember, a circuit is just a bunch of paths that eventually you could start at one spot, go along the path, and eventually return back to your original spot. And it doesn't mean there has to be just one loop. It could be you go along and then it splits into multiple roads. As long as they all come back together and lead back to the same spot, it's called a circuit. Um, and my discussion in class was about how the amount of paths there are affects the resistance. And I used the example of deers walking in the woods along some particular path as they went from wherever they're, might wake up in the morning or whatever. And maybe there's a water source somewhere where they want to walk to with their as a group. Um, I was giving that as an example. If there's one path, literally just one path, one. I mean, I have to be straight, but just one physical path from where they start to the watering hole, and there's 12 deers. If they're all kind of right next to each other or one in front of, especially if they're one for electricity, it's more like one behind the next. It could actually be more like both. Some are next to each other moving forward for electrons, but there's also layers that go back, kind of like a two-lane highway, I guess. There's cars driving together, but there's ones behind them still going forward. Anyways, if the deers are all only given one option, which was that one path, then more than likely it'll take them longer to get the watering hole. If there's 14 of them walking along one path, all pretty close together, compared to if there was 5 different paths from that branch off from where they started, and there's 5 different paths now that eventually converge back to the watering hole, because now those deers can spread out 5 deers and 5 paths. I said 14, but just imagine there was 5 deers and 5 paths. And technically each deer can take one path. And now that deer doesn't have to compete with anybody for space. Deer can move much faster. And the same could be said for all of the paths, because there's 4 other deers on 4 other paths. And they're all able to move much faster and arrive at the watering hole at the same time in less total time to go from the original spot to the watering hole, compared to, again, if there was just one path, right? Makes sense. That totally makes sense, right? When there's more path, it's easier for things to move from one point to another point. And we in electricity, again, refer to that idea as resistance. Resistance generally is relating to the level of difficulty something experiences as it moves from one point through some paths and arrives at another point. That resistance can actually be affected by 3 things. The resistance they feel along that path as they're trying to go through could depend on the thickness of the resistor, which we talked about in class. Like a thick straw will finish a Dunkin' Donuts iced coffee more quickly than a thin straw, because more water can move through a thicker straw. So there's not a lot of resistance. It just moves through very quickly, empties your cup quickly. Where a thinner straw is more resistance. It's harder for the water to move through the thin straw. Or walking through the hallway, not a lot of resistance, but if the hallway all of a sudden constricted down to a little hole and everybody had to kind of crawl through it, it would go slower, right? Makes sense. That the physical thickness can affect how quickly the stuff flows. The second thing is the conductivity of the metal. Again, I use analogies, but they're all in reference to electricity, which is flowing through wiring, right? But conductors can be manufactured to be made of different materials, different types of metals, and different materials and different types of metals have different levels of ability to allow electricity to flow through them, different levels of conductivity. Some metals like silver and gold have outstanding conductivity. Electricity can flow through them super easily, experience very little resistance. Some other metals, maybe like aluminum, you can still get electricity to flow through it, but it doesn't flow as easily through aluminum compared to as easily as it flows through silver or gold. So you'd still call all of them conductive, but you'd be like silver and gold are well more conductive. Not as much resistance with silver and gold. With the aluminum, to be more resistance because it's harder for the electrons to flow through aluminum than it is through silver or gold. That's a property thing. It depends on the properties of the material. The third thing that can affect the resistance is the number of paths, which I was talking about before. So it's the thickness of the path, what's inside the path. Is it mud or sand, or if it's people walking, like the thickness of the path, what the path is made of, metal, different types of metal, and how many paths are there. And those are the three things that affect, again, how long it takes to go from one spot to another spot, and most importantly, how well it moves and how fast it moves as it goes from one spot to another spot. And so I've set up an experiment here just to illustrate that idea. Remembering that the circuits that I showed you physically in our simulator, one is called a series circuit, and I have two circuits set up here. So this first one right here, there's two types of circuits. One is called a series circuit, one's called a parallel circuit. This is called a series circuit that we're seeing right here. This is, I know, a series circuit because electricity comes out of the red side, the plus side, and then it doesn't have any opportunity to make a choice in terms of which direction to go. It's always just, hey, go forward. Everybody has to just go along the same path. There's no split in the road, a fork in the road. So that's how you know it's a series circuit. And the series again means one after the next. And so we would say that these two bulbs, there's one here, here's one here, that these two bulbs are in series with each other. The electricity enters one and then flows out of that one and goes directly into the next, one after the next. That's what series means, like TV series, one episode after the next. So this is a series circuit. And then next to it, we have what's called a parallel circuit. Similar, but different, right? Now what we have is still electricity coming out of the positive side, flowing along, but here's the split in the road. This is where some of the electrons, remember electricity is the flow of electrons, can decide to take this path, which is, back that up a little bit. They can decide to take this path now and go down this road. Other electrons, when they reach this junction here, some will head down the black one. Others will just continue straight and take this other path. And then over here, those two flows recombine to form one more flow. So if this is water flowing like a river, some water goes down this little stream, some water goes down this stream over here, but then the two streams kind of converge back together, and then you get a much stronger flow of water in this branch right here, because right there is where they come back together. Those two flows come back together. And this again is what we call a parallel circuit, because you can think of these two paths, this middle path and this outside path, as they're not really parallel because they're not straight lines, but we still consider those as two paths that are relatively running parallel to each other, because either path allows them to move from one side across to the other side in a parallel way, right? And so again, series circuit, parallel circuit. And what I wanted to point out is that these are the same wires. They're different colors, but nobody, that doesn't affect the conductivity of what's inside. And conductivity, they're all, I'm just going to point out, they're all the same thickness. Just trust me, I'm not lying. All of the wiring, they literally come from the same, other than these. These ones are thicker. These two mains are thicker. But after that, they're all the same type of cord, and the same thing over here. They're all the same kind of cord. So any differences that we're about to see in a moment, it can't be due to the wiring being different in both. Technically, there is more wires here. Technically, let's see, 1, 2, 3, 4. Right, 1, 2, 3, 4, 5 actually, and then in this one we'd end up with 1, 2, 3, 4, 5, 6. So yeah, all right, not exactly the same amount, but that extra wire is not going to provide the difference that we're going to see. More or less, it's the same amount of wires, same types of wires. Both have two thicker ones at the mains, and then they're thinner wires after that. Also, we have two bulbs in each. We have one bulb, two bulbs. That's our series side. And then on this side, two bulbs as well. One bulb, two bulbs. So we have the same sockets. They're all the same sockets on both sides. They're the same bulbs. They both have two power sources. They're both plugged into the wall, into 120 volts back there. They both have the ability to control how much of that 120 volts that comes from the wall gets applied into the circuit with this little knob that I've shown you in the past, and it has a V there to indicate I can control the voltage with this knob, turning it right or left. Right will increase the voltage, left will decrease it. Now I know you see the opposite, so from my view, which is of course seeing it not without a mirror effect, this says 0.20 volts. I'm sorry. Yeah, I thought I was saying 0.02. It's saying 2.0. 2.0 is 2 volts. Anyways, so they both have the same power sources and ability to control how much voltage is being applied to the circuit. Now, the overall part of what I'm trying to teach again is that these two paths, I shouldn't say that, take that back. These two circuits have different kinds of paths, right? This one has no branching effect paths. This one does. Series has no branching, just one path. This has multiple paths. This has two paths because again, after it arrives here, this would be like path one. This bottom one is path two, and then they recombine over here and flow back in that blue one back into here, and then keep going, and it just repeats. So this one again has two paths. This one has one path. So which circuit has more resistance? Think of the deers that I was talking about. Do the deers experience more resistance when they're walking along one path as a group, or when they have multiple paths to use collectively to all arrive in the same spot? The deers will, for sure, if they could speak, would tell you it's much easier for them when they all have their own path and there's multiple paths. So that one can take one path, another can take another path, and that, wow, it's easier for us. We don't have to compete with each other and bump into each other, and we can kind of move much more quickly, right? Again, it makes sense. So in electricity, it's the same concept. The electrons feel more resistance as they move through this one path because they're just jammed into one path and they're closer together and bumping into each other, and it slows them down. That is one of the reasons why the current, because you'll notice that on this one, which is 0, I know you're seeing a mirrored effect, but this says 2.0, 2 volts, and the other one also says 2 volts. So those have the same voltage. I've set them to the same pushing. The pushing force that pushes that flow through both is the same in both. And it's the same two bulbs. And it's the same wires. The only difference is, again, the wiring choice that I chose, whether I decided a parallel configuration or a series configuration. And you'll notice that though all of those things are the same, the current is not. This one, which is the series circuit, the one that has higher resistance because there's only one path, has only 0.17 amps flowing when the voltage was 2.0 volts. This other one also has 0.2 volts flowing, but it actually has, I know that's confusing because you're seeing a mirrored image, but just trust me what I'm saying. This is 0.2 volts. This was also 0.2 volts. This one actually has 0.5 amps. This is mirrored, but in my view, this is showing a half an amp. 0.5 amps is flowing through the circuit that has more paths, and this one doesn't have 0.5, it is 0.17. That's like, well, half as much would have been 0.25, so it's less than half as much because it's 0.17, right? So if we could see them like the simulation where we could see the electrons moving, we'd actually see the flow of electrons as much slower along this one, like deer are moving much slower because there's only one path. And on this one, you'd see the motion being much more quick. And that's, again, higher current here, which was a half an amp, versus over here, which is only 0.17 amps. Remember, that difference in that current flow can't be because of the voltage, because they have the same voltage on both. It can't be because of the bulbs. They're all identical bulbs. Can't be because of the sockets. The sockets are all identical. Can't be because of the wires. The wires are all identical. The only difference, again, is the amount of paths, right? And so this proves that, again, numerically at least, that because we see numerically, again, that the current was far higher over here, 0.5 amps. Is numerically a value that's convincing me, and hopefully you, that if there's a greater flow here, then this parallel circuit must have overall, the whole circuit has less resistance to the flow of electrons. And since this one has less current, this circuit has slower, less flow overall, because the whole circuit overall has more resistance. Got more resistance and less flow. Less resistance and more flow. More resistance, less flow, series circuit. Less resistance, more flow, parallel circuit. So the numerical value convinces me, and we can see that the bulb, since we remember that the brightness of a bulb is affected by how much current flows through that bulb. Just shutting the lights off. So when you increase the current that flows through a bulb, make it flow through the bulb more quickly, more amps, the bulb gets brighter. So when you look at these, now that I've shut off the lights, you can clearly see that the side that has the parallel circuit, not only, and I haven't changed this has just been sitting there on, like I haven't changed those dials since I started this video. Those are much brighter. Those are parallel. Those are much dimmer. Dim, bright. Dim, bright. Why is this one dim again? There's more resistance here. There's more resistance on a series circuit path. There's only one path. And it has less current. Again, I numerically confirmed that, right? By just looking, seeing it was only 0.17 amps. And then again, on the path, the one that has multiple paths, there is the parallel circuit. Again, numerically confirmed that it was more current, not 0.17 amps, a half an amp. And that matches with the fact that it's brighter. Those two are brighter, right? So that is the lesson, that the configuration in terms of series versus parallel has a massive effect on how much power is delivered to the things that are inside your circuit. If these were speakers, if this was a stereo system and each bulb it's a speaker, and this is like the receiver that people have at home that's pushing out the electricity to those speakers, then this situation, parallel, setting up your speakers in parallel, are going to give you far more volume, because for speakers, they're not using the energy to make light. Of course not. That's only for bulbs. For speakers, they're using the energy to make sound. So this would give you much louder speakers if you wired those speakers this way. If you wired the speakers this way, you're going to get much quieter sound, less energy. Other examples might be, if there was motors, or these are little electric motors that spin, which I wish I did now that I think about it. I have motors. It might be, you'll just have to take my word for it, because it would take me a few minutes to find them. But there's a little electric motors that you just connect these wires to, and as soon as electricity flows through it, there's a little spindle thing that it spins. That's what electric toothbrush is. As long as electricity is flowing through it, that's why you have to recharge those electric toothbrushes. There's a little tiny motor in there that has a little spindle, a little thing that sticks out and rotates. And then you just put your brush on that part, and it spins, right? So my point is, if you had two electric motors in here, these ones would be no lights, take away the lights and just put two electric motors. You'd hear them. When they turn on, you hear the spinning, like, and then this one, you'd have two electric motors, identical motors, and you'd hear them, and they wouldn't be spinning as fast. Because again, lights are dimmer in this situation, speakers are quieter in this situation, motors are slower in this situation. It's just a low energy circuit. And this one's more energy, okay? And bulbs are brighter, speakers are louder, motors spin faster. I will say that if this was taken out, these power sources, which again are plugged into the wall, drawing the energy from the wall, and we're instead just connected to two batteries, and I put a battery here and a battery here, and just connected each of these, one to the plus side of the battery and one to the negative side of the battery, did the same thing over here, and just allowed the batteries to power these. And those two batteries started as identical batteries, both with the same voltage, let's say two 6-volt batteries. Which one do you think would die first? When you replace this, actually, remember these are 2 volts on both sides. So if I replaced it with two batteries that both were also 2 volts, take these things out and just put two 2-volt batteries here, it'll look identical. Flow of current is exactly the same. The brightness of the bulb is exactly the same, because the bulbs don't care who's pushing the electricity, whether it's coming from the wall or it's coming from batteries. So you'd see the exact same result. However, which one would kill the battery first? Which setup would kill your battery first? This one's pulling energy out more quickly, and we just know that because they're bright, right? And light is energy. Electromagnetic radiation is what we're talking about. That carries out energy and heat. These are also warm to the touch. So there's also, heat energy coming from those. But this one is sapping energy from your battery more quickly, because remember, current is flowing faster out of this circuit, the one that's parallel circuit. So current, the flow of current is kinetic energy. So if they're flowing faster out of this one, and the flow rate, how quickly it flows, is related to how much energy, how quickly energy is being drawn from it, then this side is going to die sooner. This one's going to run out of its electrons first. Because voltage on the battery is related to how many electrons are stored up, like a sponge holding water, and they both have the same. But this thing is shooting out electrons more quickly, which is why they're flowing more quickly, which means that sponge is going to dry out more sooner, which means for the battery, it's going to die first. And that makes sense. This is like, putting all of your wood all at once on the fire. You're going to get a lot of energy. All the wood is going to burn all at once. You'll have really bright, really warm fire, but it will die out in 5 minutes. This is more like not putting all of your wood on the fire at the same time. This is more like adding a little piece each few minutes. It's going to be a quieter, dimmer, not as warm fire, but it would last an hour, right? So I'm just pointing that out. For wall examples, we don't usually think about it dying because, walls don't die. We continue pushing electricity. But pointing out, later on in your life when you're dealing with potentially, some of you will, not all of you, cars or boats, and quads and dirt bikes and stuff like that. And your wiring, if you happen to be somebody that does that kind of stuff and you're wiring stuff, this situation, again, is desirable because people want things that have a lot of energy. They want lights to be bright. They want speakers to be loud. They want every motor to move things very quickly. But just be aware that if there's nothing recharging that battery, this battery is going to die out pretty quickly. And this one, again, everything will be more low energy, but this battery would last a lot longer in the situation with the series circuit. All right, that concludes this lesson. Hope that helps you a little bit in your understanding of circuits, series circuits, parallel circuits. Definitely provide a lot of differences in terms of the result of the flow and the power that's being delivered to the things that are connected. And just you should know that for that reason, they kill batteries sooner, but most of the things in our lives that have batteries are constantly being recharged, so nobody really cares. For the most part, everybody just wants things to be able to be fast, bright, loud. So for that reason, pretty much everything that's wired up in your life, in your homes, inside your cars, those are all wired in parallel to the car battery. So the lights, the radio, whatever, motors that move your seat up and down, all of those wirings that nobody thinks about and nobody sees, it's all hiding behind there. They are all wired with parallel circuits to the battery so that the flow of electricity is fast and it delivers strong power to all of the things in your car that need electricity. Same thing for houses and pretty much anything. Anything that you think about, that you look at, that there's electricity flowing in there, it's all parallel. Not only is there an advantage there, what I'm just saying, but as was suggested in my other class, the other advantage is that when one path breaks, it isolates the problem to that path. So all of the other paths remain intact. And then you have to just send somebody out to fix that one path. And during the time they're fixing that path, all the other paths are still flowing. And those things are all still on. That's, again, the idea of like a power outage, like we talked about in class, where, a tree comes down in the winter and hits one of the lines. Well, the whole town is broken. It's all wired in parallel. All of the different houses are all wired in parallel, and they're all broken into little sections. And usually when one tree comes down, it'll wipe out one of those little sections. When you go to the maps to see like where your town is, how many people are without power and stuff, you'll see the map and you'll see like green, 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 red. Like there's clearly an image, an image is showing there's damage here, which means that one part of the overall parallel circuit has been damaged. They're going to send a crew out, but damage there doesn't shut out the whole entire state. Right? That wouldn't make sense to do that. Everybody else is fine. It isolates the issue there. People go out to fix it there. Those people are brought up and powered up again. Everybody else never even knew what was going on. Right? And in our body makes sense too, because if something gets hurt neurologically in your body, then it's just going to affect that one part. It's not going to affect your whole body. If everything in your body was wired in series, then as soon as that thing gets damaged, your whole system would shut down. Which, maybe just pointing that out, I guess it should have. Go back here and just unscrew back to the series. I guess I should light back off. If I unscrew one of the bulbs over here on the series side, as soon as I unscrew this one, let's see what happens to that one. Obviously, this one will go off because I'm going to unscrew it, but the question is what happens to the other one? Not so easy to do with one hand since I'm holding the camera in my other hand. There it comes. See, there it goes. It's off. So as soon as I pull this out, that other one shuts the whole circuit down. That wouldn't be good for our bodies again, because if everything was wired, nerves all went from one area directly to the next area, directly to the next area. As soon as one area is damaged, like the whole system's going to shut down. On this side, however, in parallel, when I unscrew one of these bulbs, what will happen to the other bulb that's there? Nothing. In fact, it's not really true. See, there was a little flicker, but it does recognize that one of the things is being removed. But the bottom line is damage here does not affect there. This loop right here still remains intact. As soon as this one goes down, this whole road here is just out of service until this gets fixed, because this is a gap. As soon as you remove the bulb, there's a gap there. Everything stops. But this loop right here couldn't care less about what's going on over here. So all the electricity, instead of it being split, like we said before, it doesn't split anymore because it knows it can't send anything through here. So it just stops. It shuts that one down, and all the electricity now just goes around this one. All right, I should have said that before. I forgot, but glad I remembered. All right, that more or less wraps up things that I didn't feel I had the time to get to with our limited remaining time before MCAS. It more or less wraps up the last things that I knew I needed to teach you about that topic. All right, see you later.